How to solve circuits the right way once and for all. This is Vache Vorperian with the Joys of Circuits Analysis, Lecture 5. These lectures are based on my book, Fast Analytical Techniques in Electrical and Electronic Circuits, published by Cambridge University Press and available online from any bookseller. In this video, I will continue with the two extra element theorem. In the previous video, I discussed the application of the two extra element theorem to two impedance elements. In this video, I will discuss the application of the two extra element theorem to two dependent sources. And in the next video, I will give the general form of the two EET. As I mentioned in my previous video, the form of the two EET is a natural and intuitive extension of the form of the one EET. So instead of giving you the proof of the 2ET first, I'd rather have you see it in action. Hence, I'm going to use a two-stage feedback amplifier comprising Q1 and Q2 to determine the voltage gain Vout over Vin. And the two dependent generators are going to be the beta generators of Q1 and Q2 given by this simple model of the transistor. With beta 1 and beta 2 being the two dependent generators, we're going to take these out of the circuit first by assuming their values are infinite, which really makes this whole thing look like an ideal op-amp circuit, because the two-stage amplifier with Q1 and Q2 each having a gain of or a beta of infinity will be like an ideal op-amp circuit with some feedback applied to it. So the analysis is going to be very similar to it when we allow beta 1 and beta 2 to be infinite at first, or to be taken out of the calculus of the analysis of the circuit by choosing their values to be infinity first. Then we are going to reinstate beta 1 and beta 2 using the form of the two EET for two dependent generators when they're taken out of the circuit initially in the reference circuit, that is, with a value of infinity. So in the first step, we let beta 1 and beta 2 go to infinity, and we obtain our reference circuit in which we show beta 1 equal to infinity here and beta 2 going to infinity here. And from this circuit, we will determine the voltage gain Vout over Vin with beta 1 and beta 2 having infinite value. With beta 1 infinity and a feedback connection, IB1 will have to shrink to 0, which means that the voltage across R pi 1 will be 0. It means that this node will be at ground potential, which means that the input voltage will appear across RS and will start a current through it, which is given by Vin over RS. That current, once it reaches this node here, will flow entirely through the feedback network and create a voltage drop across RF given by Vin over RS times RF with the polarity as shown. Now, since the voltage here is at ground potential, the voltage across RF will appear entirely across RE, and it will start a current through RE given by this voltage here divided by RE. And the sum of those two currents will be equal to the emitter current, which in turn, with beta 2 being infinity, means that the base current is 0, and therefore the emitter current will be equal to the collector current, which is the output current. And once you have the output current, you multiply that by the load resistance, you will get the output voltage. So we write those equations down here. Beta 1 infinity means IB1 equals to 0, which means V pi 1 equals to 0. That's the voltage across R pi 1. So the current through the source resistance RS Vin over RS is the same as the current through the feedback resistor. Now, with beta 2 infinity, the base current in the second transistor is 0, which means that the output current, or the collector current, is the one that's flowing in the emitter, which is given by the feedback current plus the current generated in the sampling resistor here, the current sense resistor RE, which is the voltage across the feedback resistor RF divided by RE, and that's shown here. This is the current through the feedback network, and this is the current through RE. The sum of those two currents is the output current. So we have for the output current, we have solved for the output current, which when we multiply with the load resistance RL gives us the output voltage, and hence we have the voltage gain V out over V in. This is the reference gain, the partial credit answer. This is ideally what you would have if you had an infinite gain amplifier. But you can see what you're doing here actually from a feedback point of view. What you are doing really is regulating the output current and not the output voltage. You're doing so by virtue of the fact that in general the emitter current is very close to the collector current, or the output current as it is. You're sampling it and you're feeding it back and subtracting it from the input current, and you're making that error vanish to zero, so that this current here will be entirely dictated by the feedback network and the input voltage, having nothing to do with the amplifier itself. That was the whole idea of coming up with this circuit. Sense the output current. You're not sensing it directly at the output, you're sensing it through the emitter, because the emitter and collector currents are nearly the same, and you're regulating the output current that way. Notice that the output voltage is not regulated. It depends directly on the load resistance RL. But that's all besides the point from the application of the two extra element theorem to this circuit here. We're going to be talking about feedback amplifier. It's a good idea to make these comments early on. We now apply the two extra element theorem for dependent sources by an intuitive extension of the one extra element theorem for a dependent source. So since we took beta 1 and beta 2 out, first we will reinstate beta 1 in this manner here according to the one extra element theorem, where it appears in the little denominator here and in the little denominator here, accompanied by a null inverse gain and an ordinary inverse gain. But since beta 1 was not the only dependent source that we took out, but also beta 2, we expect beta 2 itself will come back in a manner similar to beta 1. Its reference value was taken to be infinite, so it also appears in the little denominator here and in the little denominator here. It is accompanied here in the numerator by its null inverse gain, and in the denominator by its ordinary inverse gain. The thing to pay attention to in this formula is that when you are computing the null inverse gain with respect to beta 1, the circuit in which you are performing that computation, beta 2 will be in its reference state, which is infinity. Likewise, in here, when you are computing the null inverse gain with respect to beta 2, the circuit in which you perform that computation, beta 1 has to be in its reference state, which is infinity in this case. The same argument applies for the denominator for the computation of Roman B1 and Roman B2. Now, we know that this is not complete, and these two dependent generators will have to come back in pairs. Beta 1, beta 2 in the numerator, and beta 1, beta 2 in the denominator, again appearing in the little denominator here and here, only because their reference values were taken as infinity each. Now, the first one, beta 1, is reinstated, accompanied by its null inverse gain, just like here. Beta 2, on the other hand, is reinstated with its null inverse gain, but this time, when you compute the null inverse gain for beta 2, beta 1 is going to be in its opposite state in relation to its reference state. In its reference state, it was taken as infinity, so now when you are computing script beta 2, 1, you have to set the value of beta 1 equal to 0. This happens when you pair them. The same is true for the denominator. Roman beta 2, 1 or B2, 1 is computed the same way as B2, except when you compute it here with the script 1 appearing in the denominator, in the subscript 1 appears in the subscript, it means that beta 1 is in its opposite state in relation to its reference state, meaning you set its value equal to 0. And this is it. In the next slides, we're going to demonstrate the computation of each of these null inverse gains and ordinary inverse gains. First, we determine the null inverse gain with respect to beta 1 using the following circuit. In it, we let beta 2 stay in its reference state of infinity, whereas beta 1 IB1 is replaced with an independent current generator pointing in the opposite direction. Having done that, this independent test current source IT, which replaces beta 1, along with the excitation of the transfer function, will null the response of the transfer function V0. Having done that, we determine the inverse gain IB1 to IT with the response nulled, and that is the null inverse gain with respect to beta 1. And this is the circuit with which we are going to be working. We replaced beta 1 IB1 with an independent current source IT pointing in the opposite direction, and we are going to determine IB1 over IT, and we'll do that in the next slide. Now, we perform our null inverse calculation as follows. With beta 2 infinity, IB2 must be 0, we said. Also, since we have nulled the output voltage, the output current must be 0. With the collector current and the base current both 0, the emitter current must be 0. Which means that, first of all the current in the feedback network will have to flow through RE, that's number 1. But with IB2 0, there's no voltage drop across R pi 2. It means that this node and that node are at the same potential. Now, with no current flowing here, the entire test current source IT will flow through RC and create a voltage drop across it, IT times RC, which will appear at this node here across RE. IT times RC therefore appears across RE, and it will start a current through RE, which is the one that's going to flow entirely through the feedback network. And that current is going to be simply IT times RC divided by RE. And when that current flows through RF, it will create a voltage drop across it, IT times RC divided by RE times RF. Now, this node here, with respect to ground, will experience a potential which is the sum of the potentials across RF and RE. Just follow the path. Oops, there you go. So the base resistor R pi 1 has a voltage across it given by the sum of the voltages across RF and RE, which when divided by R pi 1 will give us the base current IB1. And that's how you can solve for IB1 over IT, the null inverse gain with respect to beta 1. And that turns out to be RC over R pi 1 into 1 plus RF over RE. All you have to write is one equation by following the null condition on this circuit here. We're done with our first null inverse calculation, and we move on to the second one. In this case, we're going to find the null inverse gain with respect to beta 2, while beta 1 is in its reference state, which is infinity. With beta 1 infinity, IB1 is 0, of course, but more importantly in this case, we see that in order to null the output voltage, the only way that's going to happen is if you set IT equal to 0. When you do that, you have to realize that there is indeed IB2 flowing from V in, from the action of V in. So the inverse gain in this case, IB2 over IT, the null inverse gain, with respect to beta 2 with the output null, IB2 being finite and IT having to be 0, is infinite. We're done with the second null inverse calculation. And finally, we're going to determine the null inverse gain beta 2, 1. In this case, we have to set the beta 1 generator in its opposite state with respect to its reference state. Reference state it was infinity. Now we have to set it equal to 0, which means there is no current generator here. Beta 2 will be replaced with an independent generator just like before, pointing in the opposite direction, and that one and the input will have to null the response, which we see once again requires that this test current source to be equal to 0. That's the only way you're going to get the output equal to 0, regardless of what the input voltage is doing. And it is under this condition that we want to determine the gain IB2 over IT. We see that IB2 is indeed finite in this case because of the input voltage V in. That will generate some current here, so IB2 will merely flow down RC because of V in. We don't care what it is, but all we need to know that is that IB2 is finite and IT is 0, so that the null inverse gain, beta 2, 1 in this case, is still infinity. Because IB2 is finite, IT is 0, so beta 2, 1 is 0, is infinite in this case as well. And we're done with our 3 null inverse calculations. Next, we will have to do the ordinary inverse gain calculations with respect to beta 1 and beta 2. Now we're going to calculate the 3 ordinary inverse gains, and the first one is Roman beta 1, given by this circuit here. In it, we've set the excitation equal to 0. This is a denominator calculation. And since we're working with beta 1, we replace the dependent current generator, beta 1 IB1, with an independent current generator pointing in the opposite direction, while the second generator is in its reference state of infinity. We've seen this before. Here now, when beta 2 is infinity, the current that it depends on will shrink to 0. When IB2 goes to 0, IT will flow entirely through RC, creating a voltage drop IT RC across it. That voltage drop will appear exactly at this node here because there's no voltage drop here. IB2 is 0. So this node and that node are at the same potential, which is IT times RC. And once you know the voltage here at this node, looking back, it's a trivial matter trying to figure out what is IB1 because of this voltage that appears here. This voltage that appears here will create a current through the feedback connection here given by that voltage divided by RF plus the parallel combination of RS and R pi. That will give you this current here. And when that current reaches here, it will current divide between R pi 1 and RS according to the current division formula. And that's the way you will figure out IB1 over IT. Very straightforward calculation. IT times RC divided by RF plus RS parallel R pi 1 is this current here. And then at this point, it will current divide according to this current division here, and you're done. You can figure out IB1 over IT, and that is going to be your ordinary inverse gain with respect to beta 1, while beta 2 is in its reference state. Let's go for the second one, rho and beta 2. And that's given in this circuit here. Now, beta 1 is going to be in its reference state, infinity, while beta 2, IB2, will be replaced with an independent generator pointing in the opposite direction. And we want to figure out the gain IB2 over IT. Well, that's easy in this case. When beta 1 goes to infinity, we said IB1 will have to shrink to 0, which means that the voltage drop across R pi 1 will have to be 0. But the voltage drop across R pi 1 is the same as the voltage drop across RS, so that will have to be 0. So there is no current in this branch flowing, as well as there is no current flowing through RS. So there is no current flowing through RF. So this potential here, all the way looking back, is sitting at ground potential. There is no potential across RE. So there is no current through RE. So no current here, no current through RE. It means that the emitter current is 0. What does that mean? It means that IB2 is the same as IT. And that means the gain IB2 over IT, the inverse gain with respect to beta 2, is equal to 1. Simple as that. So we figured this one quite easily. One more left to go. And here's a surprise for you. And we now calculate the last of the 3 inverse gains. And that's going to be Roman beta 1, 2, as shown in this circuit diagram here. In it, I'm going to calculate the inverse gain with respect to beta 1, while beta 2 is in its opposite state in relation to its reference state. In its reference state, it was infinity. Its opposite state is 0. Now I want to calculate the gain IB1 over IT. As you can see, this is going to be a straightforward current division from IT through a ladder network. The first current division is between RC and R pi 2 in series with RE in parallel with RF in series with RS parallel R pi 1, followed by another current division. So you have 3 current divisions, and that will give you the gain IB1 over IT. This is our first current division, this is our second current division, and this is our third current division. Straightforward. Now the question is, why did I calculate B12 as opposed to B21? The reason is that in the last term of the 2EET, whether it's in the numerator or in the denominator, it makes no difference. What you are doing is you're pairing beta 1 with beta 2. When you pair beta 1 with beta 2, each one is accompanied with its own inverse gain. Beta 1, when you take it first, it's accompanied with the inverse gain with respect to beta 1. The second one, which is beta 2, is accompanied with its inverse gain, but with the first generator in its opposite state. But I can pair it as beta 2 beta 1. So the first of the product of those 2 inverse gains will be the inverse gain with respect to beta 2, while the second one will be the inverse gain with respect to beta 1, while beta 2 is in its opposite state. The 2 are the same, meaning Roman beta 2 times beta, Roman B12, is the same as Roman B1 times Roman B21. It's also the same thing for the script betas. It doesn't make any difference whether it's a null inverse calculation or an ordinary inverse calculation. And the thing that doesn't make a difference is the order in which you take them, 1, 2, or 2, 1. When you do 1, 2, this is the way the inverse gains will multiply out. If you do the order 2, 1, this is the way the inverse gains will multiply out. And since the order doesn't make any difference, this product here is identical to this product here. Even though they may look different, they're identically the same value, same things. And that's called the redundancy relation, about which I will be talking more in the next video. And they're very useful, these redundancy relations, sometimes to simplify a calculation, because one will be simpler than the other. And sometimes a product may have an indeterminate form. One may be 0 or infinity, and the second one will be 0 in one form, but when you reverse the order, that indeterminacy will go away, and it will not appear. Sometimes you have to do the other way around, only to remove an indeterminacy, and sometimes you do it because you judge that one form looks simpler than the other form. Now, we showed in the previous slide that Roman beta 2 was 1. So that it can't get any simpler than that. Whereas beta 1, Roman beta 1, has some kind of an expression in it. So I would guess this is a simpler form. This looks simpler than this one. And that's why I decided to compute Roman beta 1, 2 rather than beta 2, 1. And that was the surprise, about which, as I said, I will talk more in the next video. But it's intuitively clear that order should make no difference, and it should not come as a surprise. So that's our answer for beta 1, 2, the inverse gain. And now all we have to do is substitute all these expressions in the 2 extra element theorem and get the full expression for the voltage gain of the feedback amplifier. So here we go, the 2 extra element theorem. In the numerator, look at the way it's been ordered. Beta 1, beta 2, and then when I pair them, I'm comparing beta 1 with beta 2, first beta 1, then beta 2. Beta 1 is accompanied with its null inverse gain, while beta 2 is in its reference state. And beta 2 is accompanied with its null inverse gain, while beta 1 is in its opposite state. And that worked out well for the numerator. When I came down to the denominator, look what I did. I reversed the order here. I first took beta 2 here because its inverse gain was 1. Pretty simple. And I thought this would yield a simpler expression had I written this as beta 1 B1, beta 2 B2, 1. So I did not want to compute 2, 1. I wanted to compute 1, 2 because B2 was a very simple expression equal to 1. This also shows that if you reverse the order in the denominator, it doesn't mean that you have to reverse it in the numerator. You can do it independently of what you do in the numerator and the denominator. Order is not important, period. It doesn't matter where you are in the numerator or denominator. So when you perform those substitutions that we have calculated, we get the following closed-loop expression for the voltage gain of the 2-stage feedback amplifier. This is the ideal gain, followed by a correction factor here, which involves beta 1 and beta 2. These are indeed correction factors because we can see it is such an expression divided by beta 1. Beta 1 is expected to be a rather large number. So this only performs a bit of an correction on unity. So this is a little bit larger than 1. Likewise for the denominator, whatever follows 1 is only a little bit larger than 1. So the overall gain will end up being not exactly AV infinity, the ideal gain of a infinite gain feedback amplifier, but it's going to be slightly less than that. And this is that correction factor that we have here. Now we can cast this expression here in terms of the other two parameters of the amplifier, of the transistor, alpha and the transconductance, whenever we see something like this, we can think of the alpha of the transistor, and whenever we have beta, we can think of GM or pi equals to beta and make that substitution and get yet another form of that expression, as I'll show you on the next page. When you perform these two substitutions, the same expression can be written now in terms of the alpha of the transistor, which is almost equal to 1, and in terms of the GM, the transconductance of the transistor. So, and we have another expression for the closed loop gain in low entropy form, as Dr. Middlebrook would say, or in a meaningful form, as I would say, in which the various circuit elements are grouped together in meaningful way, series parallel combinations of resistors and terms added to unity for easy comparison. So this is a demonstration of the two extra element theorem applied to two dependent sources for a two-stage feedback amplifier. Thank you.